Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the second lecture of our week number 9, where we are talking about nuclear fusion. In all the earlier modules, we have restricted ourselves to the topic of nuclear fission, because that is the most predominating power generating technology, or I should say that is the only power generating technology that has been adopted by the industry so far from nuclear point of view. However, fusion, as we have already seen in the previous lecture, is something that can be of even larger importance if at all we can master the technology itself, because fusion offers several advantages over the fission reaction. Like, as a quick recap to the lecture 1, we have seen that fission offers much larger power density compared to, or I should say fusion offers much larger power density compared to fission. Like a very simple fusion reaction involving deuterium and tritium as the reactant is able to produce something like 17.6 MeV of energy, which gives an energy density of about 3.5 MeV per nucleon. But if we compare that figure to a standard fission reaction, something like one involving uranium 235 or plutonium 239, you will be getting the same figure, that is amount of energy produced per nucleon, something like only 0.8 to 0.85 MeV. So, the energy density in a fission reaction that we get is only about 1/4 of that of what a fusion is capable of producing. Also, the products of fission generally are radioactive in nature, therefore, they go through a series of radioactive decays till they reach some kind of stable isotopes. Of course, a contribution from that radioactive decay of that fission products is energy, but that also creates a lot of problem with the storage of the waste fuel, because some of the isotopes which are available in the spent fuel can have very long half life, therefore, they can retain their activity for a very long period of time, causing a problem to the storage issue. But in case of fusion reaction, we can say that there is not that much of issue related to the spent fuel, because the product of, like the one that is already there on the slide, the product is helium 4, which is an inert gas. So, that will not have any kind of nuclear or chemical activities, and hence we can easily liberate that or release that to the atmosphere without bothering about any kind of encroachment. Another big issue that we can get with fusion, or I should say another big advantage we can get with fusion, is in case of an accidental scenario. Of course, all these discussions that I am doing here, assuming that we have a proper fusion reaction or fusion reactor. Like in case of a fission reactor, if we have some issues and we want to shut down the reactor immediately, that will become very difficult to do, because of course, we can use our control rods to completely zero down the neutron flux. So, there is no fission reaction, but there will be radioactive fission products, and they will keep on decaying. They will be producing both energy and some further neutrons over a very long period of time. Still, there is even a single radioactive nucleus present inside the reactor, we shall be having that problem of radioactivity. That is something what happens in that Fukushima power station in Japan, because there, because of the power shortage, or because which was instigated by that tsunami which happens in 2011, there are no power to operate the main cooling water pump, and as cooling water supply broke down there, their control system also was not properly able to take care of this neutron flux. But even if the control system had operated properly, they would have only eaten up all the prompt neutrons available inside the reactor, and also the reactors which were already available from earlier reactions. But the neutrons which will be freshly produced because of the radioactive decay of these fission fragments, it is not possible to take care of that by any kind of control equipments. So, stopping a fission reaction under emergency situation needs to be something very well planned. Of course, under the generation 4 initiative that is being done, but older reactors face this issue a lot. But in case of fusion reaction, there is no such issue, because the product that we are getting from the reactor or from the reaction is not at all radioactive in nature. That is more often than not there you will find a stable isotope, and so if we want to stop the reactor, we can immediately do that. Also, the quantity of fuel that is available inside the reactor is very small compared to the mass that we can have inside a fission reactor. So, removing that small quantity of fusion fuel is also not a very big headache. Therefore, fusion can definitely be much more advantageous from power generation point of view compared to fission. But we have seen that the most common fuel that we can have for fusion is deuterium. Deuterium can participate in 4 different kinds of fusion reaction, 2 of them with deuterium itself. It can also participate in fusion reaction with tritium or helium-3 isotope. We have discussed in detail about the sources of deuterium and tritium. Deuterium is naturally available in seawater, or I should say heavy water is naturally available in seawater by a small fraction, which can be harnessed following quite a few technologies are there. We have discussed about one of them, which is capable of enriching the water up to about 20%, but for further enrichment we need to apply some kind of specialized technique like distillation or advanced distillation. Those techniques of heavy water enrichment or water enrichments are generally quite secret, and that is why we are not in a position to discuss even further on that. But the countries which are most involved in heavy water production generally are Canada and India. While Canada have nowadays stopped their most of the heavy water producing unit, India have, if I am not wrong, at the moment India is having 6 heavy water processing plant, or number may be 8 also, because 2 of them were under maintenance or some late commissioning part very recently. So, India is not only capable, as most of the Indian thermal power stations are based on PHW, so India need the heavy water for its own nuclear reactors, and nowadays India is also in a position to export reactor grade heavy water, because they are capable of producing more heavy water than is required by their own plants. Tritium, however, is not available in nature. Tritium needs to be bred from either lithium or from other sources, but lithium is the most common one. Lithium is abundant in the earth, and therefore, generally every fusion reactor core is covered by a blanket of lithium that offers a couple of advantages. One is that does not allow the neutrons to leak out of the fusion core, thereby protecting from the proliferation of radioactive elements or neutrons. And secondly, the neutron which gets absorbed in the blanket, when it strikes lithium 6 or lithium 7 depending upon its energy level, it can produce tritium. Lithium 6 can be converted to tritium or can be used to breed tritium by neutrons of any energy. However, lithium 7, which is a more abundant isotope, that requires fast neutrons only. So, tritium can be produced from lithium. Then we discussed about nucleosynthesis. Nucleosynthesis refers to a chain like this, where from the very light isotope or from the lightest possible isotope, through progressive fusion reaction we can produce much heavier isotope. Actually, it is extremely important, because nucleosynthesis is the process by virtue of which the entire universe has been created. at the start of everything, I do not want to go to the Big Bang theory or something like that, but it is sufficient to say that at the start of this universe, we had only those elemental components like protons and neutrons, and they were able to fuse with each other, like as you can see here, two protons or two hydrogen nucleus can combine to produce a deuterium, which can combine with another hydrogen to produce an helium. And then once we have two helium 3 isotopes, that can lead to the formation of one helium 4, and this chain can continue to produce successively heavier elements, and the most important one of them, as we have discussed, comes from that 3 alpha reaction, which leads to the production of carbon 12, and as a byproduct of that oxygen 16, and generally carbon and oxygen are the two most important components for the development of life on earth. So, nucleosynthesis is an excellent example of fusion reaction or progressive fusion reaction, and we ended our last lecture discussing about the Coulomb barrier. Coulomb barrier talks about the electrostatic repulsive force that a deuterium and tritium faces when they are able to, or when they are about to collide with each other. Just for the as we are going to discuss more about this Coulomb barrier and the option of overcoming that, so I am just repeating the same slide which I had at the end of the last lecture. The proton, or I should not say proton, the deuterium and the tritium nucleus, which are trying to collide with each other or interact with each other, they face primarily two forces. One is the electrostatic force, which is a long distance repulsive force, and its magnitude is inversely proportional to the square of their distance. So, the closer they become, the higher will be the magnitude of this force. The other is a nuclear force, which is an attraction force, but is a very short ranged one. The particles, that is deuterium and tritium nucleus, needs to be very close to each other to come under the action of this nuclear force. And the energy barrier that these two nuclei needs to overcome is something referred to as a Coulomb barrier. And while we have discussed about 4 different kinds of fusion reaction involving deuterium, the Coulomb barrier corresponding to this particular one, that is the DT reaction or deuterium tritium reaction, that is the smallest, that is only 0.1 MeV, and that is why this despite having 2 different kinds of DD reaction, the DT reaction is the most prominent one. If you remember those 4 reactions that I have mentioned in the last class, we can have 2 different kinds of DD reaction. In one case, the product is a helium 3 and a proton. In other case, the product is an helium 4 and a neutron. I am sure, like if I write quickly 1 H2 producing 2 He3 plus neutron. So, helium 3 and neutron can be one set of product, and the other set of product can be I was actually wrong, the other set of product can be 1 H3 plus plus proton. So, there can be 2 kinds of DD reaction. In one case the product is tritium, other case the product is helium 3, and both the cases we generally have quite low amount of energy production. And there can be another kind of fusion reaction involving deuterium, which is between deuterium and helium 3, which produces energy larger than this DT interaction. But this one we are repeatedly discussing about, or this is the most popular kind of fusion reaction because of 2 things. Firstly, the Coulomb barrier corresponding to this is very small, or the smallest among the 4, which is just 0.1 MeV. In fact, it is the smallest possible Coulomb barrier that we can have in any kind of fusion reaction involvement. In even for a DD reaction, the Coulomb barrier is larger. And the second advantage of this one is it also produces quite high amount of energy, which is less than a deuterium helium 3 reaction, but when we consider the corresponding Coulomb barrier, this is the best one to have. And also helium 4 is the most likely product of such a fusion reaction, because as the graph shows, helium 4 is some kind of anomaly, as the generally on this side, as the mass number increases, binding energy per nucleon increases continuously apart from this helium 4, because helium 4 is having higher binding energy per nucleon compared to the next atom or next nucleus in line, which is lithium 6. From quantum theory, this can be explained that all the 4 nucleus, 2 protons and 2 neutrons, which helium 4 comprises of, they can all remain at the ground state, and therefore, that provides the highest binding energy per nucleon for this one among all the lighter nucleus. And as the product of this DT reaction is also helium, that is another reason for this to be the most likely kind of fusion reaction. Now, this is the magnitude of that Coulomb barrier that we can have. Here UC refers to the magnitude of Coulomb barrier, and this is a simple reaction that we get by applying the Coulomb's law of electrostatics. Here Z A and Z B refers to the atomic number of the 2 particles involved. Once we are talking about a DT reaction, both Z A and Z B are 1, because both of them are actually hydrogen isotopes. R A and R B refers to the radius of both the nucleus. In this particular theory, generally both of them are assumed to be to have or to look like a sphere of slightly varying radius, and the radius you can go back to our earlier module, that is our module number 1, where we have given an empirical relationship between the radius of a nucleus and its mass number. So, generally assuming it to be a sphere, corresponding relation was can be used to get this value of R A and R B. E is small e refers to electronic charge, and epsilon is the permittivity of the free space, which is 1 by 4 pi capital K. Here this K refers to the Coulomb's constant given by this value. So, epsilon, magnitude of epsilon can also be calculated, and this particular portion E square by 4 pi epsilon actually is a constant, and depending upon what kind of reactions we are talking about, using parameters for A and B, you can calculate the value of U c, the Coulomb barrier. Now, this is a pictorial representation for a proton-proton interaction. Here again both elements are same. So, Z A and Z B are 1 and R A and R B again both are same. So, that refers to the estimated or approximate radius of a typical proton. And you can see Coulomb repulsive force being inversely proportional to R square. As the radius decreases, or I should not say radius, it is the center to center distance between the 2 proton decreases, this force continuously keeps on increasing till this particular instant. This is the instant where you can say that the nuclear force suddenly becomes dominant over the repulsive force, or you can also say that the protons have now entered the domain of nuclear force, and hence you will find a rapid reduction in the value of this U, which will allow successive proton-proton interaction. Hence, in order to overcome this barrier, this Coulomb barrier, the nuclei must have sufficient amount of energy, so that it is able to reach this particular zone, and once it is able to reach there, then nuclear force will facilitate the fusion reaction. But the energy, it needs to have sufficiently high amount of energy, and energy means kinetic energy only, and as for such kind of particles, temperature is a direct measure of the kinetic energy. So, we can clearly say, or we can explicitly mention that both deuterium and tritium needs to have high temperature, or they should both be in a temperature, in an environment of high temperature. But high means what? From in the very first slide of this particular lecture, this particular module, or this not this lecture, rather the previous lecture, I have mentioned that to facilitate fission, we have 2 or more nucleus coming together to get fused into a single nucleus, but both of them need very high energy. That high energy term was there, which is because of this Coulomb barrier, or in an effort to overcome the Coulomb barrier. Now, we have to check This high energy or high temperature refers to what kind of magnitude. But before that, a few terminologies. One is reaction cross section. Reaction cross section is a measure of the probability of fusion reaction as a function of the relative velocity of two reacting nuclei. And reactivity, generally for a given energy level, both the nuclei can have a good distribution or a distribution from 0 to infinite, a distribution of velocity. So, we often need to integrate it over the entire range of velocities, and therefore, that is why we use this reactivity. It is the average product of distribution and velocity over the entire range of involved velocities. And if we plot that with temperature or with energy, we get a distribution like this. As the temperature keeps on increasing, reactivity keeps on increasing till it reaches some kind of maxima for this. Please do not, you can ignore the scale for this temperature for the moment, because we shall be developing this magnitude very shortly. But one thing you can check here, that three kinds of reactions are shown, and for all the temperature or energy levels, the DT reaction shown by this blue line is exhibiting a much higher reactivity compared to the other two. And in this scale, it is a logarithmic scale, and that is why, say if we talk about this particular, if we talk about a level like this, you can clearly say here why the reactivity is only about the order of minus 25. For a DD reaction, it is at least 2 orders higher for a DT reaction, and the reaction rate is given as N1 N2 into the reactivity, where N1 and N2 refers to the nuclei density for both involved particles, which generally is deuterium and tritium. If both the involved particles are identical, like in case of DD reaction, then we can also write this as just as n square by 2, because here we are talking about the same particle and we do not need to go for any kind of averaging between distribution and velocity. Now, for a given energy level, again the particle can have wide kind of distribution like shown here, which can often be represented like this. And this is the PE refers to the distribution of energy, and from here we can also get the distribution, the maximum distribution of velocity of the particle or the most probable velocity of the particle, and the RMS velocity of the particle. This is the most probable velocity and this is the RMS velocity, and these two expressions are quite standard from the kinetic theory of gases. Here small k refers to the Boltzmann constant, capital T is the absolute temperature, and m is the mass of that concerned particle. And this expression, this distribution of energy is given by the Boltzmann distribution. I am not going into the details of this, because these are all standard in kinetic theory. Now, to overcome the Coulomb barrier, kinetic energy should be greater than the corresponding repulsion, and accordingly we can write that the kinetic energy of the particle, which is half into m into V RMS square, should be greater than the UC that we have. So, RMS velocity is this one. So, we can clearly write this, the kinetic energy is placed half m into 3 k T by m, which should be m cancels out. So, it is 3 k T by 2. This should be greater than this UC. From there we can say that the temperature should be greater than 2 of the UC divided by 3 k, and UC it was given in the previous slide. Once we are talking about deuterium and tritium, we can put Za and Zb equal to 1, and we can use suitable values of Ra and Rb corresponding to deuterium and tritium. K is Boltzmann constant. So, putting there we get some idea about the value of the temperature, which may be involved or which we have to provide in order to overcome the Coulomb barrier. And do not be surprised with this number. This temperature comes to be something greater than 10 to the power 10 Kelvin. We are talking about a temperature of the order of 10 billion kelvins, just to facilitate the interaction of one deuterium and one tritium isotope, and that is where the challenge lies with fusion. From the very beginning only, I am repeatedly saying that if we at all can control the fusion reaction, then it will be very advantageous, and the control issue is here. achieving this temperature is near impossible as per the present day technology, but everything is not that grim. Let us proceed further. There are couple of factors which says that the value of temperature that we are getting, this may be over prediction, because one factor comes from the Heisenberg's uncertainty principle. It says that, as all of you know from the school level physics, that the particles momentum and position both can't be predicted together with certainty. So, there is always a finite possibility that once the energy level is given, the particles position can be anything, and hence even with an insufficient energy, the particle may can breach through the barrier and reach the other side to have the interaction. And another probability which is more mathematical, the values of this radius that we are using, those are more empirical in nature, which are obtained from classical mechanics. But in practical point of view, this radius value or this radii value may not be correct, because the zone of this strong interaction can practically be much larger than what we get in theory. The effect of these two factors is a reduction in the required temperature level. A temperature of the order of 10 to the power 10 Kelvin we are getting, considering a very simple kind of mathematical framework, but this Heisenberg's uncertainty principle and also this possible over prediction in the radius value of this radius values of the nuclei, the correct value of temperature may actually be lower. Without going into the detail of the kinetic theory, the quantum mechanics, just we can say that the wave function associated with a free particle must be continuous at the barrier, and that will show an exponential decay once it passes through the barrier. The wave function must also be continuous on the far side of the barrier. So, we are saying that as the particle is passing through, it is having a high wave function, this is the amplitude of that, and on the it is continuous. On the other side of the barrier it is also continuous, but there will be an exponential decay in between. That is the amplitude of the particle oscillation that will decrease inside the barrier, and the magnitude that can be something like this. So, there is a finite probability that despite having insufficient energy level, the particle will tunnel through the barrier. This is sometimes called tunneling, which refers to this reduction in the wave function of the particle while it is passing through that Coulomb barrier. On reaching the barrier, particle must satisfy the Schrodinger equation, which is of this particular form. Here h bar refers to Planck constant divided by 2 pi, or you can say 2 pi into that is that number is a Planck constant. H bar is Planck constant divided by 2 pi, or Planck constant is 2 pi h bar. M is the mass again, E is the energy level, and U naught is that same Coulomb barrier that we are using. We could have represented this one with U also, and psi is the corresponding potential. So, this is a quite as others are constant, like h bar Planck is a constant, M is a constant, and U and U naught is also a constant for a given interaction. And if we fix up the E, then it gives a very simple solution where this alpha is having this particular form. With all this consideration, that is those which are shown in the previous slide, and also whatever solution we are getting from this Schrodinger equation, the outcome of that, the energy requirement for nuclear fusion for both deuterium-deuterium and deuterium-tritium collisions can be dramatically lower or drastically lower than the Coulomb barrier. That is, if we calculate the energy like we have done in the previous slide, we have just calculated or tried to do a balance between the kinetic energy and the Coulomb barrier, or we have considered that the kinetic energy has to be greater than the Coulomb barrier, and accordingly got a velocity level and hence the temperature level. But because of this tunneling kind of actions and also possible wrong prediction of the radius of the particles, we can actually see that practical value of temperature requirement may not be that much of or may not be that high, may be slightly lower than that astonishing figure that we have got in the previous slide, and that is applicable for any kind of fusion interaction like DD or DT reactions. But still the numbers that we may get, that will be quite substantial. Presently the particle energies that we can get in case of thermonuclear reactors is in the range of 1 to 10 keV, and this is a figure that we can say in the center of mass frame of reference. If we calculate the energy, the cross section in that particular what we can achieve at the moment, that is 1 to 10 keV, refers to something in this level of this, and the corresponding cross section is still quite significant. Of course, there is still improvement, like if we can go up to something like 20 keV, we can get even larger cross section and so a larger reaction rate, but at least for DT reaction this is still quite significant. But 1 to 10 keV is also not a matter of joke. How to calculate the corresponding temperature? We know that the particle energy can directly be related to the kinetic theory, that is kinetic energy, that is half, I should not put this in here, half m into v square should be equal to 3 kT. From there we can calculate the temperature just as E by 3 k, and putting the numbers into the corresponding formula and also associated things, we get 1 keV to correspond to something like 0.77 into 10 to the 7 Kelvin, which is still more than 1 million Kelvin, means we are talking about 7.7 million Kelvin temperature, and 10 keV even one order higher, 0.77 into 10 to the power 8 Kelvin or 77 million Kelvin. Just to put that into perspective, the temperature in the interior of the sun is something like 0.15 into 10 to the power 8 Kelvin. So, that is just something like 4 to 5 keV talking about. So, we are in order to facilitate, despite all these corrections and advantages that we are getting because of the tunneling effect etc., still the temperature range requirement that we are talking about, that is extremely high, and that can be higher than the temperature that we may have inside the sun, even to get a 10 keV of energy level. So, the temperature requirement is the biggest issue that we can have in order to facilitate a fusion reaction. We somehow have to produce that level of temperature, and another issue is that whenever we reach that level of temperature, all material turns to plasma. So, handling the plasma is another very big issue. But temperature alone is not the only one, rather there is something called the critical ignition temperature, which refers to fusion ignition, which refers to the ignition the temperature requirement or the point where the reaction becomes self sustaining. That is, we somehow have to initiate the reaction once and also provide some desired level of conditions, but once the reaction starts, the amount of energy that will be coming out of the reaction, that should be sufficient to continue the reaction itself. It is something like that chain reaction, means to initiate the fission process we have to strike an uranium-235 isotope with a neutron, but once the fission happens, then it will emit a few neutrons, and if we can provide proper condition, then at least one of those neutrons will be able to induce fission for another U-235, that way sustaining a chain. The same applies here, and if we can provide the conditions properly, then we can reach a condition where the energy yield from the fusion is sufficient to sustain the reaction, and hence no further external energy source will be required. But temperature satisfactoring the temperature alone is not sufficient, rather we have to consider a few other factors also so that we can overcome all possible losses. One is the confinement time. The plasma must be maintained at that temperature above the critical ignition temperature for a certain period of time, then only it can reach that self sustaining period. If we are able to achieve this critical temperature only for a very short instant, just for a pulse, then it may not be sufficient to have a self sustaining thing. Other is the ion density. A critical density of ion must also be maintained to have this high probability of collision. So, temperature, confinement time and this ion density all together leads to this condition of critical ignition temperature or self sustainment. In order to provide a sufficiently high temperature to enable the particles to overcome the Coulomb barrier, therefore, we have to provide high temperature, a sufficient confinement time and also a sufficient ion density, so that we have a net yield of energy from the fusion reaction. A part of that is sufficient to continue the reaction and rest can be utilized for the downstream application purposes. And that condition generally is given by a product of ion density and the confinement time, condition often referred as the Lawson's criteria. And this is the condition for a DT fusion. The product, actually this should not be written like this, should be n into tau. The n into tau, this product should be at least 10 to the power 4 second per centimeter cube, and for DD reaction again it is just n into tau, it should be greater than 10 to the power 16 s per centimeter cube. So, this Lawson's criteria is something which we have to provide, that is we must provide sufficient ion density and also we must provide sufficient amount of confinement time, so that the ions are exposed to a sufficiently high temperature over a long period of time, and hence it reaches a situation where the energy yield is sufficient to self sustain the reaction. So, critical ignition temperature, it is quite it is just analogous to the critical temperature that we it is quite analogous to the criticality condition that we get in case of fission reaction. There we must ensure the criticality, that is the reactivity should be equal to 0 or multiplication factor should be equal to 1, so that we can sustain a chain reaction. Just same here, this, but here condition is given in terms of this product of n and tau and also in terms of temperature. Finally, we come to thermonuclear fusion. Actually, there are quite a few ways the fusion has been conceptualized, but I repeat, at the moment there is no commercial fusion reactor which we can depend on. Rather, there are quite a few research reactors which are giving newer inputs about the fusion reaction and the possibility of having fusion as a commercial source of operation. Maybe we are going to have commercial fusion reaction in near future, but at the moment we are depending mostly on the research reactors. And also I could have put in lots of more data at this point, data from quite a few research reactors or whatever research outcomes that we have, but this being more a fundamental course. So, I thought about just giving you an introduction to the thermonuclear fusion, the thermonuclear fusion reactors, and if you are interested about the topic, you can explore further. So, the biggest challenge in a thermonuclear fusion is confining the hot plasma. Once we can attain that critical ignition period, we know that the fission reaction is possible, but before we can reach that level, all the particles, because of that high temperature that reaches the plasma level, and handling hot plasma is extremely difficult. So, the requirements, firstly, the plasma should not come in contact with any kind of walls. So, it must be located in a vacuum. Secondly, as the temperature is high, pressure also will be high. So, we have to handle extreme conditions of high pressure and high temperature. And also the plasma, because of this energy interaction, will try to expand, and therefore, we must provide some kind of force to resist this expansion. That force can be of different kinds, it can be gravitational force, it can be magnetic force, or it can be an inertial force, and accordingly we can have different kinds of confinement structures. Gravitational confinement, that is the amount of mass that is required to have a gravitational confinement is not possible at the earth, rather it is possible only at very large stars. The thermonuclear fusion is generally the mechanism that stars go through. Means at the initial level of their birth they had only hydrogen isotopes or only proton, and because of the nucleosynthesis they are continuously going on forming heavier isotopes like from proton to deuterium, from deuterium to helium, helium to even heavier things like lithium or carbon or oxygen, and some of the stars are even reached very high mass number level, something in the range of irons. And as you know, iron and nickel are the isotopes which are having the highest level of binding energy per nucleon. So, they get stabilized more or less there, which actually also leads to a loss of the energy that the stars are able to emit, and hence in a way that indicates the starting of the death of those stars. But coming back to this point, gravitational confinement is more relevant to those stars, but not for technical point of view. What we commonly find is a magnetic confinement. Electrically charged particles follow magnetic field lines. So, a strong magnetic field is provided to confine the plasma. Here strong refers to extremely strong. Actually, the problem of handling a plasma or the issue of handling a plasma leads to all possible extreme conditions: extremely high temperature, extremely high pressure, and also extremely high magnetic field. All these three together leads to a real tough technical problem, which we hope will be solved in near future. And the final one is the inertial confinement. It apply a rapid pulse of energy to a large part of the surface of a pellet of the fusion fuel, causing it to simultaneously implode and heat to a very high pressure and temperature levels. This is something that researchers have started to work on, and may show a proper good demonstration in near future, or if it is at all able to give a good demonstration, then it can also be thought as a future option. But presently all these are still under research. The knowledge base is still quite limited. While we know completely about how fission happens, what are the things that we need to control fusion, but we are yet to reach that level of technical advancement, so that we can actually control that reaction. And also the fusion reaction, like fission reaction, can be controlled or uncontrolled. It is again quite similar to that critical, subcritical or supercritical, like in case of fission reaction. A controlled reaction is where the rate of reaction can be controlled to a fixed level, but an uncontrolled one is where the rate of reaction keeps on increasing rapidly. And I hate to utter the term, but the example of an uncontrolled reaction is a hydrogen bomb. That is an example of a fusion reaction, but an uncontrolled one. So, that takes us towards the end of this particular module. Again I repeat, I have not added any technical data or any information or analysis which is too tough. This is a primary level course, and so I am keeping informations only to the basic concepts. But to summarize the topics that we have discussed, we have seen that fusion offers significantly higher energy density compared to fission, and deuterium is the most common fuel which can go through 4 different kinds of fusion reactions. The DT reaction or deuterium tritium reaction is the most preferred one, because it shows a small Coulomb barrier and also it gives a reasonably high amount of energy. Seawater is the most common source of heavy water, whereas tritium can be obtained from lithium breeding, and in order to overcome the Coulomb barrier, very high kinetic energy is required, which essentializes extremely high temperature level. And because of that temperature level, all the material gets converted to plasma, making it very difficult to handle that. Temperature, confinement time and ion density together determines the self ignition characteristic of a fusion reactor. And finally, very briefly we have mentioned the magnetic confinement is the common option in present day research reactors. So, that takes us to the end of our module number 9. I would wait for your questions. If you have any queries, please keep on writing to me. I will try my best to answer to you. So, I am signing off from module number 9. In the next week, we shall be discussing about the effect of radioactivity on biological substances. Thank you.